Zhenghan Wang, who's really one of the most visionary, I think, researchers in the field of topological quantum computation, and I'm extremely eager to hear his thoughts about all this.
Thanks, Frank, for all the arrangement. Actually, it didn't occur to me this incredible connection between what I'm talking about, Turing, at this place. I'm in Cambridge. And I think Turing is one of the very top of the scientists and mathematicians I really admire. And I want to talk about something which more abstract than my job, which I work for Microsoft, so I'm still both in industry and in academic. So Turing actually, I really admire him for all the incredible things he did, but incredibly the fact that he's a mathematician. At least I think that's the truth. So I'm not a historian. So when I prepared my talk, I started to search who was the first person who formally wrote down the word Church-Turing Thesis. And I chased down to this book by Stephen Klein. She's a logician. He wrote a famous book called Introduction to Mathematics. I don't really recommend people study mathematics, but that's the book. And he wrote down this paragraph. For those who are not aware of the history, that both Klein and Turing were students of Alonzo Church, a famous logician in Princeton. And so I'm a big fan of Turing, so I read his book. I should get back to. So I read the English version by Andrew Hodges. I own the Chinese version. I didn't read it. A friend gave it to me because they knew I'm a fan of Turing. And this is, of course, the movie. Many people probably watch it. So in the book of Andrew Hodges, he said that actually Alan Turing knew quantum mechanics really well. That's actually always a question for me. Did Turing ever think about quantum computing? It's very natural. And my speculation is yes. And he came to the conclusion, which is I will tell you, there's nothing there for him. So the point is that if you want to think about computability, which means you don't care about efficiency, just you want to know what is algorithm. Quantum computing will give you nothing new. Everything can be computed by a quantum computer, can be computed by a Turing machine. It's just slow sometimes, but doesn't matter. Just multiply matrices, I can do it. So I kind of speculate, I don't know if I can find any evidence Herbert Turing came to this conclusion, which is, if you want to talk about something computable, and you want to talk about computer you can build, classically, there's only one thing you can do, which is Turing machine. So that's the so-called Church-Turing Thesis. If you want to talk about computability, algorithm, nothing to talk about else, it's Turing machine. And then people extended to say, okay, maybe everything can be computed efficiently, can be computed efficient by a Turing machine. That's the thing now we don't believe. So most people now believe there's a counterexample, which is quantum computing. And this can do computation more efficiently than classical computers. So that's what this quantum computer is about, which is the issue of computability is unique. There's Turing machine there, nothing else. But they want to talk about efficiently computing, there are two possible different ways, classical and quantum. And they are potentially different. And like Frank said, as a scientist and mathematician, we want to prove anything. I don't want to speculate. We cannot prove that, but that's a possibility. But I want to talk something slightly different, which is I call the quantum extended Church-Turing Thesis. I believe many people knew this, but I think I might be my co-author now, I might be the first one to write it down formally, which is if you want a new mode of computing using quantum mechanics or quantum field theory, there's nothing new either. There's only one model of quantum computing. So if you think about it, what's the most experimentally verified quantum theory? Has to be quantum field theory. We don't have a mathematical definition, but that's the most experimentally verified. If this thesis, the new thesis, stated the quantum thesis correct, and then that says quantum field theory, which means relativity plus field theory, infinite degree freedom, will give you nothing new in terms of efficiency of computing. So that's what I will try to convince you and make the case that this is a possibility. I don't know how you want to ask questions. You're free to interrupt for any clarification or question. We're happy to take any question. So I want to start with a general philosophical question. So what is computing? What is the power of a physical theory? If you think about what is computing, so it's a very simple process. So as a mathematician, we beautifully formalize computing. It's just a family of a function from bit string to bit string, and the length of the bit string goes to infinity. So that's a computing problem. I think it's given by Pythagoras, says everything is a number. We just encoded everything by number, and then write it in base 2. And then a computing problem just a function. And now if, say, you give me a theory, how do I compute a function? It's very simple. You give me the input x, I will make this into a state of my physical system. And then evolution will do the computing for me. And then I will just measure in the end. That should be my answer. If I'm smart, the answer should be encoded in there. That's the computer programming. So formally, that means any physical theory will select a class of functions which can be computed efficiently. So that's the thing I call XP, just for fun because I work for Microsoft. So every physical theory, in principle, select a class of functions which you can compute efficiently. So what is quantum computing? Quantum computing, it just says, okay, you want to compute a problem? You give me the input with a bit string, and then I make it into a quantum state. And then I do evolution with just unitary matrices. And then at the end, you multiply the state from the beginning by the matrix, and then you measure this state. And if you're smart enough, you will see the answer in the measurement. So the whole point is it's just a unitary matrices, but there's a catch, which is in order for this to be a computer problem, you have to break this big unitary matrix into small steps. And that's the idea of a gate. So this matrix is just a quantum circuit. So as I said, basically every physical theory gives you a complexity class. And if you have classical physics, that will give you the class P, which is the classical efficient problem solvable by classical computers. And for quantum mechanics, the class is called BQP. The question?
Yeah, could you say something about the three-body problem in gravitation? The three-body problem in classical physics.
Are you thinking about classically or quantum?
Yes, only classically.
Classically, I think I would just say, I have an assumption. Any physical theory is computable. If it's computable, it will be computed by a Turing machine. Do we have an efficient classical algorithm to solve the problem? I don't know. A lot depends on formulation. It's just like factorization. That's a classical problem. We don't know there's a classical efficient algorithm to solve it. But we do know there's a quantum algorithm to solve it. So if it's a computable problem, it's done, according to Church-Turing Thesis. But if it's efficient, we don't know. That's pretty much the PNP problem, like the salesman problem. So the conjecture or the extended quantum Church-Turing Thesis is saying that quantum field theory gives me no extra computing power. So the class of efficient function computable by quantum field theory is the same thing as quantum mechanics. So that would be BQP. BQP stands for bounded error quantum polynomial time. So you might ask, what about other theories? I don't know. String theory is a different kind of thing. I don't know what's the class function we can compute, and also it's very difficult to formulate because it's not a unitary theory at this point, so we don't know really how to formulate. As a mathematician, I want to deal with rigorous quantum field theories. So I don't want to speculate or anything because that's really tricky. So if you ask, what is the experimentally relevant, rigorous defined quantum field theories? There are not many. So there are two large classes, topological quantum field theories and conformal field theories, in particular in two dimensions, 1 + 1 dimension. There are some other theories, but it's normally not unitary, so you don't really know how to deal with it as a computer theory. So I will focus on those two classes, which are topological quantum field theories and conformal field theories. All my theories are unitary because I want to do quantum mechanics. And if the quantum extended Church-Turing Thesis holds for quantum field theory, in particular will hold for topological quantum field theory. And that's actually a theorem. So that's what I did with Michael Friedman, which was my thesis advisor, and Alexei Kitaev, physicists probably know. And Michael Larson was my colleague at Indiana University. He's a number theorist. So we have this theorem basically says the quantum extended Church-Turing Thesis does hold for topological quantum field theories. So whatever the class of efficient computable problem, solvable problem by topological quantum field theory, that's the same thing as quantum mechanics efficient solvable problem. Actually, historically, my advisor Friedman speculated he wanted to be the other way around. He wanted QKFT computers more powerful than quantum computing. It turns out he didn't get it. It's the same thing. It suddenly has to how to formulate the problem realistically. So, so this is mainly what I'm going to tell you, which is how to prove the quantum extended Church-Turing Thesis for topological quantum field theories. My passion actually is on the one I don't know, which is conformal field theories. So I really want to redo everything I have done for QKFT, and then unfortunately I don't have much to tell you about conformal field theory, but I will tell you where the difficulties and why this is an interesting problem.
Kind of moving to this conformal field theory, can you just give a couple of ideas what?
I will talk at the very end when I finish the QKFT.
Okay.
What's the problem and how to deal with it. So first I want to mention a little bit about how I think about quantum field theories. So this is one of the most exciting things to ponder about, which is quantum field theory absolutely is correct, but why we don't have a mathematical framework to do it? We all see electron, photon, they work perfectly fine. Why the theory is not consistent? I have no answer to that question, but I do want to think about it in the way I want to use it. So for those who know the mathematical formulation of quantum mechanics given by von Neumann, so this is a strict, direct formulation of quantum field theory using the von Neumann axiom for quantum mechanics. So if you give me any space-time, so this is the difference from quantum mechanics. Quantum mechanics only talk about space. Here we're talking about space-time. You give me any space-time, I'm supposed to give you a Hilbert space. And this normally will be infinite dimensional. And normally you need a foliation for this X in order to write down this Hilbert space. And then having a composite system, which means you have two disjoint space-time. If you have Hilbert space for each of them, and then the composite system will have the tensor product. And then measurement is the same. It's always a Hermitian operator. But obviously, not every Hermitian operator is physical. There's a Heisenberg uncertainty principle. But mathematically, we just say every Hermitian operator is a potential measurement. And evolution is slightly different. So in the quantum mechanical formulation, evolution is just e to the th. H is a Hamiltonian, so it's a unitary transformation. Here, it's slightly different, but it's a space-time. So what you have is a representation of the Poincare group. So it's a Wang circle representation there. In principle, this is a mathematical rigorous formulation of a quantum field theory, just that this really tension, if you give me a formal definition of moment, it's useless. It's rigorous, but there's nothing you can do. So now I can formulate the question about what I mean by quantum extended Church-Turing thesis for quantum field theory. So basically you want two things. You want all quantum field theories to be efficiently. The whole point is efficiently, because it can be simulated by Turing machine. Therefore, also can be simulated by quantum computers, but I want this to be efficient. And the second thing is, I want the quantum computer also to be efficient by quantum field theories. You would say, that's a triviality. Not quite. So actually, that's how I got into this thing. So you would think quantum field theory contains quantum mechanics, so therefore it has to be true. But it's not that straightforward. So that's basically I want to address. And now, more mathematically, how do you simulate each other, quantum field theory and quantum mechanics? So I will do this a sandwich picture. So if you have a quantum field theory, suppose you have a Hilbert space of your space-time, and then also you have evolution of this space-time system. And then what you want is, you want to find qubit space, both inside and outside, so that this is a sandwich in between. And then you want any evolution here can be simulated by this side. That means this can simulate quantum field theory, can be simulated by quantum field theory. If this commute, that means quantum mechanics or quantum computing can be simulated by quantum field theory. The subtlety is, how do you do this embedding? And they have to be efficient. And then the most difficult thing is, how do you do experiment? How do you do measurement? Because that always has error, and that's always probabilistic. And to formulate the approximation, that's probably the most difficult thing. But in principle, that's all you need to do, just simulate each other. So now I want to tell you something really can be done, which is mathematically how to do this mutual simulation of top-order quantum field theory with quantum mechanics or quantum computing. So there are two things you want to simulate. There are the evolution, and there are the partition functions. So in top-particle quantum field theory, the evolution are discrete. So these are discrete representations of the mapping class groups, in particular the braid groups. Those are the things on the disk. And then the partition functions are quantum invariants of three manifolds or link inside three manifolds. So the angle I went to top, this whole thing is actually think about the Jones polynomial. So there's a theorem that I believe is also down here. I think it's Welsh. So he and other people proved that if you want to evaluate the Jones polynomial of link as a particular root of unity, that's actually sharp P hard, which is as hard as you can get for computing problem. But there's a catch, which is that is done exactly. So you have to get a Jones polynomial value exactly. And if you want to do really quantum mechanics, you don't get exactly answers. You get approximation. So that's what this top-order quantum computing is formulated using TQFT. And to do this, we need to go through something called Witten SU2 Chern-Simons theory. And this is probably the most famous or well-known top-particle quantum field theories. And there's another big story which I will skip, which is top-particle quantum field theory is supposed to be effective theory of top-particle physical matter. So those are the things which are very exotic, but it does exist in nature, like fractal quantum Hall states. So those are top-particle physical matter. This Witten Chern-Simons theory, SU2 theory, actually are effective theory of top-particle physical matter. So what's the most interesting about top-particle physical matter is actually anyons. So anyons, those only exist in 2 dimensions strictly. So these are particles. Of course, the anyon, the terminology came from Bragg-Wilczek. So he played the game of we have particles which are bosons, we have particles of fermions, and now you have something, anything goes. So that's called anyon, and exists in 2 dimensions. So what are they? So these are just excitations, and they are elementary excitations. So if you have somebody like me, really does not believe that there's a difference between, so-called fundamental particle and emergent particle, and then these are just generalization of boson fermions. So the excitation of the vacuum. And the only thing is, if you believe fundamentally vacuum, that particle called elementary particle, and my vacuum is very complicated, it's a very dirty piece of material, but they are also elementary excitations. So, so they are just finite energy elementary excitation. And the thing interesting about anyon is that in boson fermion, if you have a multi-body wave function, if you permute a boson, nothing happens to the wave function. If you permute a fermion, you get a -1. Actually, this is the wrong statement. It completely does not make any sense, but I won't go into it. It's the standard way to say it, but it does not make sense. And for anyon, if you do it, there are 2 cases. For abelian anyon, you get a root of unity. For non-abelian anyon, you get a matrix. So that's the non-abelian part. The statistics, the matrix, the unitary matrix. Now, this has a beautiful mathematical theory called unitary modular tensor category, which is my favorite thing to study. Spend like more than 2 or 3 decades on this word. So, but they are just like, if you want to believe like me, they're just like the electron and photons. You create them from vacuum. So let's assume we have this magic topological phase of matter, and we have these anyons. So then what do? So this is basically a cartoon picture of the whole topological quantum computing. So I claim quantum computing, which is equivalent to topological quantum computing, which is equivalent to something very simple, which is take all the links and you try to approximate the Jones polynomial at the 5th root of unity. That's all a quantum computer can do, and that's also what it is. So how this works? Assume you have a topological phase of matter which give you anyons, which give you the Jones polynomial at the 5th root of unity. Actually, there are a few exceptions, 1, 2, 3, 4, 6. And other than those numbers, everything else will work like 5. And for those who know crystals, that's the planar symmetry of the crystal. But I can never make a theory out of it. It cannot be random, but just something. But let me, for concreteness, so definitely let's take the 5th root of unity. And then topological quantum computing is nothing but this picture. So what do? So you have your topological phase of matter. So let's say you put on the plane. And let's assume you control there's no anyons in there. There's no excitation. It's inside the ground state. And then you inject some energy. Just do something. You create some anyons. Assume you are so good at control it, you create them at certain places with a certain species, which is the Jones polynomial 5th root of unity. And then you do the braiding. And then you measure it. And when you measure it, you take them pair and you fuse them. And then you just, every time you fuse it, you inside the lab, you look at it and say, oh, does this pair of particles kill each other, go back to the ground state, or something else come out? And you just sit there, repeat this process, polynomial many times. So this probability of everything goes to the ground state, you can calculate that approximate the Jones polynomial of this link, which is a braid, and then you just close them up, called plot closure. And the complexity of the computation is given by the complexity of the braid. And the theorem says anything you want to do, like break RSA 2048. Nobody has done this, but it would be fun to do it for an undergraduate. You can write down a braid, and then this process will give you the factorization, and vice versa. So that's this theorem tells us that the whole quantum computation is nothing but this process if you have this magical material. Unfortunately, we don't. So that's basically top part of quantum computation is. It just create anyons, control them, annihilate them, then see if they go back and repeat polynomial time. Everything in quantum computing has to repeat polynomial time just to boost the probability of success. And this is equivalent to quantum computing. So now address the question, why this works for QKFT and why it does not work yet for conformal field theory. So I assume people here all know the quantum circuit model. It's a two-dimensional Hilbert space that ties them together. In particular, it's a finite dimensional Hilbert space. So one thing about QKFT is all the Hilbert space show up is finite dimensional. But life is not always good. And the problem is they have no tensor product. But you can just choose some random one, it still works. So, and then the mapping class group, at least the braid group, they have this elementary braid. And that's basically gives the idea of a gate. So there's a canonical elementary step, which is just braiding. And most important, actually, there's a locality of topological quantum field theory. And that's not obvious, but there's something called Green formula, which is the fundamental property of a quantum field theory. If you have a quantum state on a manifold, you can reconstruct by knowing the restriction to local patches. That's called locality. It's not necessarily tensor product. The tensor product is very artificial. That's a great. I think I will be. And then I think I only 2 slides. So the most important thing is topological physical matter is gapped. So what gap means is that the ground state, the excited state, has a definite amount of thing in the thermodynamical limit. So that's make sure that the idea of statistic makes sense. There's nothing in the world exact. Real numbers are not real in the sense nature just does not give you. That's infinite precision, infinite energy. That's exactly Turing Thesis trying to tell us. So the gap tells us we can tolerate noise, and that's the protection. And now back to the question, I have one more slide to say to make a connection to the program. There are lots of beautiful mathematics to be done in topological quantum computing, and I can on and on, but I just want to mention 2 things. So this is a program of boundary, impurity, and defect. And I can make boundary into topological quantum computing. I can make defect into quantum computing, but I don't know how to do impurity. I don't know what topological impurity means. And I wrote lots of paper on gap boundaries, lots of paper on defect. There's extension from anyon to gap the boundary to topological defect. The topological defect is done by a former student of mine, Colin Delaney, and gap boundary was done really by a former intern of mine, Iris Khan. So you can extend those things there. But I don't even know what's the meaning of topological impurity, and I don't even know how to do quantum computing with it. So now address the CFT question. So I want to go to the most difficult part, gapless. So a conformal field theory is totally different from a topological quantum field theory, that it is gapless. Actually, gapless is a generic phenomenon for quantum field theory. Quantum field theory kind of model critical points. So gapless is the generic case. Once you have a gapless theory, and then you can ask the question, how can be ever a gapless theory stable? The only thing I can think of has to be symmetry. So there's a symmetry there. And if you want to turn this into a computing problem, as I said, you have to talk about representation, you have to talk about correlation functions, and then you realize they're all infinite dimensional, there's no obvious generative set, no obvious Green formula. So I just don't even have a starting point how to formulate. But if I really want to give a talk on this, I have one way to do it, which is using anionic chains. But that's not the time to talk about today. But that's what I'm working on, really I'm excited about. So the last slide of my talk is there's a practical interpretation of the quantum extended Church-Turing thesis. As Frank said, we don't really know to build a quantum computer is a scientific problem or it's an engineering problem. But if you think about it, if you want to build a quantum computer, you have to work with all kinds of materials, neutral atom, ions, superconductors. They don't follow quantum mechanics per se. They follow quantum field theory. So material that really modeled by quantum field theory. So if you want to build a quantum computer, in a sense, that's quantum field theory simulated quantum mechanics. And the opposite way, as Frank said, we want to know if you have a quantum computer, what do you want to do with it? So I don't have a good answer to that, but my analogy is to build a quantum computer in the near future, and I'm convinced can be done. It's like the early days we tried to build a telescope, a microscope. We just want to see something. And what do you want to see with a quantum computer? It's just quantum field theory or quantum materials. It's just a simulation. So I want to borrow my advisor's comment to answer the question, what do you do with a quantum computer? His comment was, if I have a quantum computer, I will just use it to build a better quantum computer, to start the quantum evolution of quantum computing. And I will stop here. Thank you for listening.
Any comments or questions? Yes.
So you mentioned like no obvious growing rules for CFTs. So I thought like let's say sequence axioms, there are some rules of how the coordinates feel, right?
I think this is corresponding to the cluster axiom in quantum field theory in general. But quantum field theory is hard to formulate, so it just, as I said, it's not hard to define something formally. It might be useless.
Hi. So I've heard that for analog classical computers, they can actually solve NP-complete problems.
So okay, so I did like many people did, which is I perfectly ruled out classical analog as a physical model. So I use the word physical to mean digital. So analog is a subtle question to discuss, actually. Quantum computing is an analog computer. But you can ask why, I believe you can be built. The difference between quantum computing analog versus classical analog is quantum computing, the computing part is analog, but the error correction part is digital. So that's the only difference between quantum computing and classical analog.
But surely there's a potential for parallel problems happening with quantum case. Like you might have CFTs have, if you have infinite dimensional Hilbert spaces, you might be able to solve QMA complete problems.
Probably you can.
But in a way that's not robust.
Yeah. The thing is,
how do you precisely formulate the quantum extended Turing thesis?
So I insist in the definition of any computer class has to build you some stability. So I reject anything like infinite energy, infinite precision. That's normally you run into. I believe so. I think any loophole I can think of, you use infinite precision and infinite energy, which you are not entitled to in your real model. So maybe.
You mentioned when we're actually doing anionic quantum computing that you can use gap boundaries. And I believe normally we use gapless boundaries when we have anions, or we use an interference experiment to get the amplitude. I believe normally. So why is it better to use a gapped boundary if possible?
There are breeding of gap boundaries.
Can you repeat it? Because I don't think the people...
So the question is, how do you do quantum computing using a gap boundary, which seems to be analog? What I'm saying is that the model is a little bit complicated. You can still braid gapped boundary where they are far apart, and you get very minimal computation power. And then you can do topological measurement, which I mean interferometer and fusion. And that's enough for you to get universal quantum computing. It's a non-trivial theorem, but it can be done.
Okay, so if there's further questions, I think we should postpone this to this discussion that we have this afternoon, actually, with all the speakers. But let's thank Zhenghan for this.